Hello, so in this video we're going to start talking through these ideas of exponentials and logarithms. Now, I really want to get under the skin about what an exponential is and then later what a logarithm is about. So in order to do that, I'm going to start off with the types of situations where you may see exponentials. Because exponentials are really useful in the real world. They're usually used when we want to understand growth or decay. So you've probably heard the phrase exponential growth or exponential decay, for example, with interest in a bank account, or if you're working with radioactivity, or if you're working with populations. I mean, a topical example at the moment, we've got the coronavirus going on, COVID-19. That is a disease which is spreading in the population, and it can be modeled using exponential growth. Okay, so understanding exponential growth and decay is a really important fundamental idea in mathematics. Now, I'm only going to look at the growth case today, so exponential growth, on the basis that if you can understand everything you need to about growth, exponential growth, you'll also understand everything you need to about decay, because decay is just growth in the other direction. Okay, so just bear that in mind, all right? Now, I'm not actually going to start off with exponential growth because in order to understand it, I want to give you something to compare that against. So I want to give you some other types of growth so that you can see what exponential growth is and why it's different to other types of growth which you may be familiar with. So I'm going to start off with a very simple type of growth called linear growth. Okay. Now, linear growth, the reason why I say it's familiar is because it follows a similar kind of principles which you've seen with equations of straight lines, so your coordinate geometry, for example. So I'm just going to write down the equation, or my growth equation. Okay, so I'm going to write it down as y equals 2t plus 1. Okay, now I should say that I've already predefined some variables over here on the left hand side. So I've basically said that I'm going to look at time. Okay, so time, if you like, is my independent variable. That's the thing which I'm having control over. That's the thing I'm changing. And just instead of writing time out all the time, I'm just going to denote that by t, the letter t. And I'm also going to look at the size, let's say, of my population at each particular point in time. So I'm going to let my size be called y. So I'm going to give it the notation y. So effectively what I'm going to do is I'm going to see the size of my population changing through time. And the equation I'm going to use is going to be this for linear growth. So y equals 2t plus 1. Now, because we've already looked at coordinate geometry, this should seem quite familiar, okay? Because have a look. It looks just like a linear growth equation, just like a linear equation. Okay, here's my y, and here's my, well, not x in this case, but it's t, so y and t, so y against t, okay? And you can see that this looks like my gradient, and this looks like my y intercept. So basically I've got an equation of the form y equals mx plus c, or in this case y equals mt plus c, because I'm just substituting x for t. Okay, so let's actually play this out. Let's see what the size of my population is at each point in time. Now let's suppose, just for the sake of argument and just for the sake of clarity, that we're working with time in years. So these numbers over here in the left column basically represent the number of years that my population has been growing for. All right, so let's have a look. So at time 0, in other words, at the very start of my time period, at the very start of my experiment, okay, what is the size of my population? Well, I just simply need to stick t equals 0 into this equation. So 2 times 0 is 0 plus 1, so the size of my population will be 1 at time 0. Let's see what happens a year later. So at year 1, I'm just going to stick 1 into this equation. So 2 times 1 plus 1, that's going to give me 3. So that's my size at year 1. At year 2, what's the size of my population? Again, I'm just going to stick t equals 2 in this equation. So that's going to be 5. And if I keep going, if I stick 3 years into my equation, I should get 7. 4 years into my equation, I should get 9. 5 years into my equation, I should get 11. Okay, good. So basically what I've got now are 2 columns. In the left-hand column, I've got what year I'm looking at. And in the right-hand column, I've got the size of my population at that particular year, so that particular point in time. Now let's just drill down a little bit. Let's see why it's called linear growth. Okay, so why is it called linear growth? Well, have a look at how my population is changing at each point in time. So from each year, how is my population changing? So from year 0 to year 1, okay, I move from a population of 1 to a population of 3. Well, that's basically an increase by 2 in my population. Okay, so that's an increase of 2. If I look at the difference between year 1 and year 2, okay, that's basically another increase of 2 because I moved from 3 to 5. If I look at the increase from, or the difference from year 2 to year 3, again, that is also an increase by 2. So basically, every single year you can see that I'm effectively just increasing by 2, okay? So every single year, I'm just basically increasing my population by 2. So what I can say then is that if I have linear growth, okay, it basically means that my population is changing by the same amount every single year. Hence it's linear, okay? It's changing by the same amount every single year. So the rate of change, if you like, is constant. Now, that rate of change is effectively changing by adding, okay? So I'm effectively adding some particular value every single year, okay? So that's linear growth. It's a simple type of growth. It's fairly just constant growth in that it's increasing by the same amount every single time period. All right, let's look at another type of growth then. Let's look at a type of growth called polynomial growth. Now, we have briefly looked at polynomials before, okay? A polynomial is basically of the form something to a power, okay? So if I take my variable, in this case t, my time, and raise it to a power like t squared or t cubed, that would be an example of polynomial growth. Okay, so if I want to look at polynomial growth, I'm just going to derive an equation for polynomial growth. So let's suppose, for example, my polynomial growth equation is going to be y equals, let's say t squared, okay? So basically, the size of my population is given by whatever time I'm at squared, okay? That's an example of polynomial growth. And in fact, I'm just going to add a constant there, so therefore we don't start off with a population of 0, okay? So let's see what happens at each time period. So let's just stick each of the time periods into my equation. Well, okay, if I start at year 0, if I stick 0 into my equation, I get a size of 1. So that's the same as linear growth so far. If I stick time equals 1 in my equation, I get a size of 2. So far, we're not actually any quicker than our linear growth. In fact, we're slightly slower because at time 1 for our linear growth situation up here, we had a population of size 3. Okay, whereas with the polynomial growth, t squared plus 1, we only have a population of size 2. But let's keep going. So 4 plus 1, that's 5. And then we're going to have 10. And then we're going to have 17, and then we're going to have 26, okay? So even though my polynomial growth started off slower relative to my linear growth, eventually I surpassed my linear growth, okay? Eventually I just outgrew that. So let's look at what's happening with each time period. So from year 0 to year 1, well, okay, in this case I'm adding 1, okay? From year 1 to year 2, I'm adding 3. Year 2 to year 3, I'm adding 5. And from year 3 to year 4, I'm adding 7. And then from year 4 to year 5, I'm adding 9. So far, this is not linear growth, because you remember, linear growth means that you are adding the same amount every single time. Whereas clearly for polynomial growth, you're not. You're adding different amounts each time. But if you bury down deep enough, so if you start looking at like second differences or third differences, this will effectively just become constant. Let me show you. So the difference of the differences between year 0 and year 1 is going to be, well, 2. And for year 1 to year 2, that's going to be another 2, and so on and so on. So basically, if I look at the second differences of what my population is changing about for each year, you can see that there is a linear sequence buried underneath that, okay? So in other words, polynomial growth is fundamentally, again, based on adding some amount each time. It's just that the amount you're adding each time is different, but if you go down deep enough, if you look at the differences enough times, then you will effectively just get a straightforward linear growth situation, okay? So far, linear growth is adding, polynomial growth is also adding as well. Now, how do these two types of growth differ from exponential growth? So let's have a look at that, okay? So let's now have a look at exponential growth. Well, exponential growth, you can see that it's got the word exponent in. Now, if you remember, exponent is literally just another word for a power, okay? So I'm going to look at growth which has powers in there. But if you notice that polynomial growth has powers, look at that, t squared, that's got a power. So what I need to do to make this different, to make exponential growth different from polynomial growth, is I need to swap what's in the power. So you notice for polynomial growth, the base is always your time, and the power is the thing which is constant, so t squared or t cubed or t to the power 4. Whereas for exponential growth, it's the other way round. In other words, the base is always constant, but it's the power that is your time. That's the thing which is changing. So let's just write down y equals 2 to the power of t as a basic example. Let's suppose this is my exponential growth situation. So you notice now that the thing is changing is in the power. My time is in the power. All right, so let's see what happens at each of these time intervals. So at time 0, are you happy that my population is just going to be 2 to the power 0? Well, anything to the power 0, that's just 1. If I look at time equals 1, that's going to be 2, so my population size is going to be 2. If I look at time equals 2, my population size is 2 squared, or 4. Time 3, population size is 2 cubes, that's going to be 8, and so on, okay? Now look what's happening each time, okay? Because this is different now to what we were looking at with our linear growth situation, where we're just adding the same amount each time, our polynomial growth situation, where we were adding different amounts each time, but buried underneath those differences, we were having a linear sequence again, so we're still adding. If you notice with exponential growth, for every time period, what's effectively happening is I'm doubling, okay? So I'm timesing by 2. And that makes sense, right? Because if you notice, the thing which is changing is now the power. So in other words, I'm changing it from 2 to the power 0, which basically means just take 1. And then 2 to the power of 2, which means 2 to the power of 1, which just means take 1 times 2. And then 2 to the power of 2, which means 2 times 2. And 2 to the power of 3, which means 2 times 2 times 2. So in other words, the power is telling you how many times to multiply by 2. And you can see that over here. So the first really important observation that we need to make with exponential growth is that it is different from polynomial growth and linear growth because we are now multiplying by the same amount each time, okay? So exponential growth is a type of growth where we multiply by a constant amount each time. So we times by 2, or times by 3, or times by 4 for every single time period, okay? Whereas linear growth, polynomial growth, the other types of growth we looked at, we were always adding every single time. So are you happy that exponential growth is nearly always quicker than polynomial and linear growth? Like, yes, okay, at the start, it may actually work out that, for example, polynomial growth is quicker. Like, look at the first 2 years, for example. We go 1, 2, and then at year 2, we're at 5 for polynomial growth. Whereas for exponential growth, we're at year 2, we're only at 4. But eventually, if we leave it running for long enough, exponential growth is always going to be quicker than any of the other types of growth that we've looked at. Okay, so that's the first really important observation. Now let's bury into this equation a little bit deeper, because do you notice that the thing which we're multiplying by every single time, in this case 2, is buried within this formula? Like, have a look. This is my size and this is my time. So do you notice that buried within this formula, we have the growth rate? So that 2 there, that 2 down there, that little base of the t, that is what we're going to be multiplying by every single time. So if you like, this is my growth rate, or my growth factor, I should really say, rather than growth rate, because we'll look at rates in a little bit more detail in just a second. So I'm going to call it a growth factor to not confuse the two. So this is my growth factor. This is literally telling me what I'm multiplying by every single time. And you can see that because I'm literally taking 2 and raising it to different powers of t. Now you remember that powers just literally is a shortcut for repeated multiplication. So if t is equal to 3, that just literally means that I've started with my initial amount and multiplied it by 2 that many times. Okay, so for t number of times. Okay. Now I want to change this equation. What if I didn't want to start off with a population of size 1? So you see at time 0, my population size is 1. What if I wanted to start it off at 5? What if I wanted to start my population off at 5? How would I adapt this equation to make sure that I start my population off at 5? Well, just notice, this part here just simply means multiply by 2 as many times as t is telling you. Okay, so multiply by 2 that many times. So if you notice, there's space at the front to put a number. And that number is what I can multiply by 2 that many times. In other words, if I write an exponential growth equation like this down, so I said 5 was my initial amount, so I want to start off at 5, and then effectively I want to multiply by 2 for as many times as my time period is, so as many years as I'm looking at, okay? So let's just make sure that works, okay? So at time 0, well, I get 5 times 2 to the power 0. 2 to the power 0 is 1. Times that by 5, that's 5, which is looking good. That's exactly where I wanted to start. Then look what happens at time equals 1. So I have 5 times 2 once, so that's going to be 10. And then at time equals 2, I have 5 times 2 twice, 5 times 2 to the power of 2. So that's going to be 20. And then at time 3, I've got 5, and I times it by 2 3 times. So 5 times by 2 to the power of 3 is going to be 40, and so on and so on. So that works, okay? So in other words, I'm still starting at a different number this time, the 5, but I'm still multiplying by 2, okay? So I'm doubling for every single time period. All right, good. So in other words, if I wanted to generalize this, we've established that this number here, the 2, the base if you like, is our growth factor. Clearly, if I change that to something different, like for example 3, then that would mean that I would be timesing by 3 every time. If I change that growth factor to 10, then it would mean that I'm timesing by 10 for every time period, etc, etc, etc. So the base, the number which is back down, it's the base of the t, is going to be telling me what I'm multiplying by every time. And then this thing here, the number which is out the front, the number which is multiplying by that, is our initial value. That's our initial population. Because it basically says start with 5 and then multiply by 2 that many times in this particular case. So this here is going to be my initial, well in this case I'm talking about population, okay? But in general it's going to be my initial value. It's going to be the value of my size at the start, okay? Whatever size I am at the start. So in general then, what I can say is that if I want to write an exponential growth equation down, it will be y, that's my size, so my size is going to be given by some initial amount, so I'm going to call that I0 to represent the initial amount, times by some growth factor, so I'm going to actually call it g, okay, to represent my growth factor. That's literally what I'm multiplying by for every single time period. And of course that growth factor, well, I need to multiply by that growth factor t times, whatever year I'm up to, okay? So in general, this is the equation of an exponential growth situation, okay? Now I did say that I'm not really going to talk about exponential decay in this particular situation, because if you understand growth, then it's just basically growth in the other direction is just decay, okay? But to adapt this formula, I will show you how you adapt this formula that we've just derived for decay. You just basically need to say, well, growth, exponential decay is just growth in the other direction. Well, that basically means that I'm going backwards in time. So forwards in time will be positive, backwards in time will be negative. So I just replace that t with a negative t. And that's talking about exponential decay. So that's as simple as it comes, okay? That's exponential growth. That's exponential decay. And it's as simple as that because, of course, decay is just growth in the reverse direction. Now let's actually look and see, what does this graph look like? So what does the exponential graph look like? Something like this, okay? Well, it's a really easy graph to draw. Let me do it in black, okay? It's a really easy graph to draw. It's basically a graph which basically doubles in height every single time, okay? So it's an ever increasing graph. It's a graph that steadily increases because for every time period, you're basically doubling the height or tripling the height, whatever your growth factor is telling you what to multiply by, okay? So basically the graph will look something like this, okay? It's a graph that is ever increasing as you increase through time. So this is t, this is y, and this is 0, okay? Now it's really important to note that the point where it crosses the y-axis, at this point here, okay, this point here, is going to be whatever your initial value is. Because if you notice, the y-axis, this y-axis, is the point when the time is equal to 0. Well, we've established when time is equal to 0, we'll just have our initial value. Okay, so this is going to be the initial value. It's going to cross the y-axis at the point of your initial growth, your initial value at the start. Okay, but you also notice that you are never, ever, ever going to be ever reach 0. Okay, so your population is never, ever, ever going to reach 0. In other words, we would say that this line here, okay, the x-axis, or in this case the t-axis, time axis, is going to be an asymptote. In other words, this graph gets really, really close to that x-axis, but it never, ever touches it. Now, if you think about it, that kind of makes sense because as you move through time, if you take the equation y equals 2 to the power of t, for example, so in that case, our initial value will just be 1, okay? If you move through time in the positive direction, we've said you're just basically multiplying by 2. So every single time period, you're multiplying by 2. So from year 0 to year 1, you're multiplying your population by 2. From year 1 to year 2, you're multiplying your population at the previous time period by 2, okay? Which means if you go in the other direction, you're going to have to be dividing by 2. So that's the decay situation. You'll be dividing by 2. Well, okay, if you start here, for example, at your initial value, and if you keep dividing by 2, no matter how many times you're dividing by 2, you'll always have a quantity to divide by 2. In other words, it will never, ever be 0. It'll get really close to 0, like you'll have a really small population eventually, but it will never, ever reach 0, okay? There'll always be something to divide in half, okay? So that's the reason why that axis is an asymptote, okay? Now, just for the sake of argument, I will also show you the exponential decay situation. We'll just remember that the exponential decay situation, we have said, well, that's just basically growth, but in the reverse direction. So in other words, this would be like y equals 2 to the negative t, okay? Well, just think about what transformation has happened there. I've basically changed the value of the t before I've applied the function. So in this case, my function is 2 to the power of something. In this case, I've changed the value of my t, changed the value of my input before I've applied my function. In other words, I have like y equals f of negative t, okay, in this case t is my independent variable rather than x, okay, so that should correspond to a reflection in the y-axis. So in other words, my decay situation will just look like this. So it's exactly the same as my growth situation, that's my growth, okay, but it's just that decay will just be happening in the other direction, but this will still be my initial value, so I0, okay. So in this case, instead of timesing by 2, I would be dividing by 2 as an example. Okay, but really it's determined by whatever your growth factor is. All right. Now, I'm just going to write this down on the screen. So this sentence here really summarizes a really important and key feature of exponential growth. It literally says, the larger its size, the faster its growth. So exponential growth is a situation whereby the bigger something is, the faster it can grow by. Now, if you think about it, that makes sense with populations. Because if you start off with a population, let's suppose the modelling situation of the population is y equals 2 to the power of t again. So in this case, the growth factor is t, okay? If I start off with a population of, let's say, 1, okay, then 1 year later, that population has grown from 1 to 2, okay? So I've basically gone from 1 to 2. But if I start off with a population of, let's say, 1 million, that suddenly grows from 1 million to 2 million, okay? So in other words, the bigger something is, the faster it can grow by. If you think about it, that makes sense because the more people that are in my population, the more the reproduction that happens, which means I'm going to end up with even bigger population the next year, okay? So exponential growth really fundamentally is about this idea. The larger something is, the faster it can grow by. I always use the analogy of a snowball rolling down a hill. So if you start at the top of the hill, the snowball is probably can fit in the size of your palm of your hand, right? It's not very big. Then as you roll it down the hill, what basically happens is that more snow can cling to that ball, which means its surface area is increasing. Now, the bigger the surface area is increasing, which means that there's more surface area for snow to physically cling to, which means it can grow even faster, okay? So by the time it reaches the bottom of the hill, it's probably a great big snowball, probably way bigger than you, right? And the reason being is because as it rolls, it's picking up snow, which means its surface area is growing, which means it can grow even faster. So exponential growth fundamentally is saying, well, look, the larger something is, the bigger its size, the faster it can grow by. So I want to talk about what its rate of change is doing. So rate of change is a really important idea in maths, which we will meet again with differentiation, okay? But rate of change is just simply describing how quickly is something changing by, okay? So in this case, I need to look at its difference in its size. So I'm going to write that as dy. So d for difference, and y is obviously representing size in this case. So change in y, how much my size is changing by, in comparison to, so divided by, how quickly I'm changing. So what time increment am I looking at? So I'm going to write that as difference in time or change in time. okay? So this thing here is dy by dt. Now, like I say, when we look at differentiation in a little bit more detail, we will become very familiar with this notation. But for the moment, all I want you to understand is that we're comparing a change in side on the numerator to a change in time on the denominator. So we're basically looking at the ratio of how our size is changing in relation to how quickly in relation to a time. Okay, so we're looking at the change in size in comparison to the change in time. Well, okay, if we look at that, we're basically saying that should be proportional to whatever its size is, okay? So the faster its growth, that's what we're talking about there, the rate of change, how quickly something is changing by, should be proportional to however big it is. The bigger something is, the faster it can grow by. That's a really fundamental idea. So we're going to write that as proportional to. So the rate of change is proportional, and I'm going to write it like that symbol there. It's kind of like a little fish. Just simply means proportional to its size. So its size, remember, we've given the notation y, okay? So we're basically saying here that the rate of change, how quickly your population is growing by, is proportional to however big it is. In other words, the bigger your population, the faster it can grow by. Now, if I wanted to convert this to an actual equation, then what I can basically say is that dy by dt, in other words, my rate of change through time, should be equal to, well, it's not quite equal to my size, okay? It's always going to be off by some constant, okay? So I'm just going to write that as k. That's my constant of proportionality, because it may be actually my rate of change is 3 times my size or 4 times my size. But it doesn't matter. It's always going to be off by some constant, some value, okay? Now, if I actually break this down and look at it in a little bit more detail, then look at this, okay? Now, I'm going to actually give you just a series of different growth situations, okay? So I'm just going to assume that in each of these situations, my initial population is 1, so I don't have to have that constant at the front every time. But let's suppose we have a growth situation like y equals 2 to the power of t. In other words, every single time period, I'm going to be doubling by 2, okay? So timesing by 2. So if I look at my growth rate, okay, so my rate of change of my growth, dy by dt, okay, that's just going to be, well, it's going to be some constant times by my size. So it's going to be some constant times by y. In this case, it's going to be 2 to the power of t is my y, that's my size, okay. And in this case, my constant, so my constant which I'm off by, is going to be 0.69. So it's going to be basically 0.69 times by 2 to the power of t. Let me just scooch that over a little bit so you can see a little bit clearer. Okay, so here's my size and here's my constant of proportionality, and I'm basically saying my growth rate is proportional to my size, it's just off by some constant. Okay, if I look at, say, for example, another one, if I look at something like y equals 3 to the power of t, in other words, for every single time period, I'm basically timesing by 3. Well, in that case, the rate of change of my size is going to be, well, my constant of proportionality in that case is 1.1, okay, 1.10 actually, times by my size, which is 3 to the power of t, okay? If I look at another situation, for example, y equals 4 to the power of t, okay, then in that case, the rate of change of my size is going to be, the rate of change of size is going to be 1.3, or 1.39 actually, times by my size, so that's going to be 4 to the power of t. So in other words, it's always going to be off by some constant. The rate of change, how quickly I'm growing by, is always going to be off by some constant of my size, whatever size I'm at. Except there's one situation, so there's one growth rate, one growth factor. So this is doubling, this is tripling, this is timesing by 4, okay? There's one situation where I multiply by an amount and it's not off by some constant, it's just off by a factor of 1, okay? So in other words, in this case, dy by dt is just not off by any constant, it's actually off by 1, okay? Times by the size of my population. So what situation is that? What base am I looking at there? It's something called e, okay? Now, e is a really special number, okay? So e is actually a number, it's not a letter, okay? E is a special number. It's equal to about 2.718, and it carries on forever and ever and ever, just like pi. You know, pi carries on forever and ever and ever and ever without ever repeating. It's irrational, okay? E is the same. It's 2.718, and then it carries on forever and ever and ever, and it never ever repeats. So in that case, if you have a base of like 2.718 something, okay, that e, then in that case, the rate of change is not actually off by some constant, because the constant is just equal to 1. So in that case, dy by dt is actually just equal to e to the power of t. Okay, it's actually just equal to e to the power of t. And that's a special growth situation, okay? Now, in this video, we're not actually going to explore where does e come from. It's basically the difference between discrete growth and continuous growth. So if you have growth that is happening discretely, in other words, it's growth that's happening every year. So the situations that we looked at the start with our sizes through time, we basically had an assumption there. So if I look at my assumption up here, for example, okay, we basically were assuming, well, okay, at time 0, my population was 1. And then for the entirety of year 0, my population stayed at 1. And then as soon as the clock ticked over to year 1, then it changed to have a size of 2. And then for the entirety of year 1, it's stuck at a population size of 2. Then as soon as the clock ticked over to time 2, then my population changed to 4. So in other words, I'm basically assuming here, inherently built in with this model, I'm assuming that my population will remain the same for the entirety of the year, and it will only change as soon as the clock ticks over to year 2, or as soon as the clock ticks over to year 3, etc., etc. Okay? Now, clearly, okay, so if you're basically saying that growth is only happening at discrete time intervals, so it's only happening at like year 1 or year 2 or year 3, and it doesn't actually grow in between those time periods, then we have a discrete time interval, okay? And this is where like y equals 2 to the power of t is a good model, or y equals 3 to the power of t, or y equals 5 to the power of t, okay? So basically if you have some base which is like 2 or 3 or 5, that's where the discrete time intervals are well modeled. But clearly, most growth is not discrete. In other words, it doesn't stay the same for the entirety of that year. Most growth is happening all the time. Therefore, it is continuous. So if you have a continuous situation, in other words, it's growing all the time, then you would use E as your base, this special 2.718. If you are interested in where E comes from, I will link a video in the description below, which literally talks you through the derivation of this. But it's literally the limiting case of a discrete time sort of situation. Okay, so that's really important. So let's just bring it back right to where we started then. So we looked at this situation. We looked at situations where our population size was growing through time. And we looked at the situation of exponential growth, okay? And we understood that if I have time, if I know how long my population has been growing for, in order to get size, I can use an equation something like this. So I naught times by g to the power of t as an example, okay? So it's basically an exponential situation. Now I'm going to use a specific example just for the sake of illustration. Now we understand what exponential growth, the general form of an exponential growth equation is. I'm basically going to assume that the exponential situation, or the exponential model that will model this growth situation is y equals 2 to the power of t. What this equation literally says is you tell me how long your population has been growing for. So you give me time. You tell me how long this thing has been growing for. I then stick it in this equation and I will be able to tell you the size of the population at each point in time. So what an exponential does is a way of saying you give me time and I will tell you how big your population is. I will tell you size, okay? But what if we wanted to ask the reverse situation? What if I wanted to say to you, well, look, you tell me how big your population is, and I will be able to tell you how long that population has been growing for. In other words, you give me size, I'll give you time. Well, that situation we can model using something called a logarithm, okay? Now, it sounds like a big fancy word, but I promise you it's really simple. It's just based on the idea of what we were doing before, okay? So in other words, in this case, I want to find time, okay? I want to find t. So in order to do that, I need to use a logarithm. So I'm going to shorten logarithm to log, okay, rather than writing logarithm down every time. But are you happy that I need to know the size? So I need to be given a size, but I also need to be told what your growth factor is every time. So what you're timesing by for every time interval, okay? So in this case, my growth factor is 2, okay? And that is also baked into the logarithm, and I just put it as a little 2 down here, okay? So just like with an exponential, the growth factor is baked into that equation. Same kind of idea with a logarithm. The growth factor is baked into that equation, and it's baked in down here as a little 2 down here. Okay, so literally exponentials and logarithms are kind of doing the same thing. It's just you're looking at things from two different perspectives, okay? So exponentials literally say, you tell me how long you've been growing for and I'll tell you how big it is. You give me time, I'll give you size. A logarithm asks the exact opposite question. It says, you tell me how big your population is and I'll be able to tell you how long it's been growing for. In other words, you give me size, I give you time. Okay, so it's really important to be aware of how to convert between logarithms and exponentials. They're fundamentally exactly the same thing. We just say that they are inverses of each other. They are inverse functions. Now, I know that we have looked at functions before, okay? So inverse functions. So in other words, so with an exponential, the input is time and the output is size. With a logarithm, the input and the output have switched. So the input now is size, the output is time, okay? So this is an idea of an inverse function. It's basically just undoing what you've done with an exponential, okay? So let's look at this in a little bit more detail. We need to be aware of how to convert between logarithms and exponentials. If I give you something like 2 to the power of x equals 5, if I want to write that in logarithm format, well, in logarithm format, you're looking at the power. Because are you happy? This number up here is corresponding to the time. It's corresponding to the power. It's how long you've been growing for. So if I want to write that as a logarithm, I would basically say that x, that's the thing I'm interested in. Well, I need to look at a logarithm, so I'm going to write log. I need to know what my growth factor is. In this case, it's 2. Okay, so I put the 2 down there. And then I also need to know the size. So in this case, the size is 5. Okay. So I would say that as, let me write it down as I say it, okay? I would say log to the base of 2 of 5. So actually I'm just going to shorten that. I would say log to the base 2 of 5, okay? So you notice the base 2 is telling me what is my growth rate, okay? What is my growth factor? And then baked into the equation, baked into how I say it, the 5 in this case is the size of my population. Okay, so the way which I would read this thing on the right hand side is quite simply log to the base 2 of 5. Okay, so quite simple and easy. Now you notice as well that I tend to put the brackets in my logarithm. You don't have to, okay? I just tend to make sure that it keeps it definitely separate from the base, okay? Because I need to know that growth factor. Okay, you don't have to do that, but I tend to just for completeness, okay? All right, so let's have a look at this in a little bit more detail. So that's how to convert between the two. So in general then, if I give you some base to some power of some number, in order to convert that into a logarithm, well, I'm interested in the power in this case. The power is all about the logarithm. That's where the thing I'm interested in is. And it's going to be log, well, I need the base, so in this case the base is b, and I also need the size of the population, so in this case the size is n. So just be aware, you need to be able to convert between the two effortlessly. Now, we've looked at the idea of an exponential and logarithm. We basically said they're exactly the same thing, they're just inverse of each other, just looking at different things. Okay, so the inputs and outputs have swapped. So let's just recall, what does the equation, let's just draw like an equation down, y equals, I don't know, let's go y equals 2 to the power of t. Let's actually see what that graph looks like, so just remind ourselves. So that graph here is going to look something like this. In fact, let me make it a full set of axes, okay? So it's going to look like something like this. Okay, so in this case, it's going to cross at 1 because that's my initial growth, that's my initial value, sorry, because the number out the front here is just 1 times 2 to the power of t. Okay, so this is my equation y equals 2 to the power of t. Okay, now if I want to look at a logarithm, so I'm not going to worry about y's and t's in this case, I'm just going to write y equals log to the base 2 of t instead. Okay, so I'm not going to, this is not actually strictly speaking, these two things are not inverse of each other, but I'm just making sure the y and the t matches up. So this is y as a function of t, and let's just make sure this is y as a function of t as well. Okay, but the idea should still be the same. So if I draw in my graph, well, let's just think. Are you happy that for my logarithm graph, I've basically said, because it's the inverse, okay, because the logarithm and exponentials are inverse of each other, it should just be the case that my input and my output should swap round, okay? So in other words, my time should become my size and my size should become my time. Well, if I do that, okay, hopefully you realize that in order to swap my t, so this is my t-axis and my y-axis, in other words my time axis and my size axis, in order to swap those two things around, I need to reflect them in the line y equals x. So I reflect it in the line y equals x, and it basically means that all of these values up here will basically, the x and the y coordinates will swap places. So in other words, if I swap that around, that there should be the inverse function. So that there should be the shape of my logarithm graph. Okay, so if I get rid of all that, that's on the left-hand side is my exponential graph. This here on my right-hand side is my logarithm graph. Now, just like before, we said that this axis was the asymptote. In other words, my exponential graph would get ever closer to it, but never ever reach it. In much the same way, because my x and y axis have now changed places, that there is also an asymptote. In other words, this graph will get ever and ever closer to it, but never ever reach it. Okay, so that's really important. And likewise, because it crosses the y-axis at 1, it means this will cross the x-axis at 1. Okay, so that there is a difference between an exponential and logarithm function. Just think, my exponential graph looks like that. I remember that. That's nice and easy to remember. My logarithm graph just reflects it in the line y equals x. In other words, all my x coordinates become my y coordinates and vice versa. Okay. Now, let's just think about the domain and range. We've looked at domain and ranges. So what's the domain and what's the range of my exponential graph? Okay, so this graph over here on the right, on the left-hand side. So in this case, my domain, well, I can basically stick any value I like in. So in this case, I can say that t can take any real number. Okay, so t can take any real number. Now, again, if you're not sure about this notation, if you're not sure what the real numbers are, I've got a good video sort of talking you through all the different types of numbers, which is well worth a watch, so I'll link that in the description below. Okay, so that's the domain of my exponential graph. What's the range? So in other words, what are the set of possible output values that I can take? Well, are you happy that I can take any positive output value, but I cannot take a value of 0 because that's on the axis, and I cannot take anything down here either, okay? So in other words, the output of my graph has always got to be positive, okay? So in that case, my range is basically saying y has got to be strictly positive. Now, happily, it's really easy to do the domain and the range of my logarithm graph, because are you happy that the domain of my, so let's write down domain and range, are you happy that because my inputs and outputs have effectively swapped places on my exponentials and logarithms graphs, then that means that the domain and range will also swap over as well. So the domain of my exponential graph should become the range of my logarithm graph, and the range of my exponential graph should become the domain of my logarithm graph, okay? But let's just check that, okay? So the domain in this case, have a look at the graph, okay? I'm basically saying that I can take any positive value, but I can't take 0 or less, okay? So in other words, all of that is ruled out, right? So in other words, the domain of my logarithm graph is basically saying I can take any value of t which is positive, but I can't take 0 and it can't be negative, okay? And that corresponds then to my range, okay? Similar kind of thing, because of course y and t has changed places now, but the domain was y is greater than 0, which means the domain should be t is greater than 0. Now let's just check for the range. Can I have any different possible output on my output value? Well, yes, I can. I can have any different possible output. So in that case, I'm going to say my range, which remember is y, is going to be a member of the real numbers. It can be any real number I like, okay? And likewise, you can see there that my domain and range kind of match up of my exponential and logarithm graph, okay? So that's the domain and range of my logarithm graph. Okay, fantastic. So let's actually start by looking at some properties of logarithms and how we can combine logarithms together. Now, before I go any further, I just need to clarify something. Usually, we write a logarithm of this form, okay? So y equals, for example, log to the base a of x, okay? So in other words, we nearly always have to have a base down there, okay? Because that base literally tells us what we're multiplying by each time. That's our growth factor, right? Now, there are situations where I can just write this, okay? Now, this is kind of shorthand notation. It actually means something else, okay? It can mean two different possible things, okay? So when I don't bother putting a base down here, what I mean is that I'm writing something that comes up a lot. So actually, because it comes up so often, I don't actually tend to bother putting that base down there. The base is kind of implied, okay? Because it's surprising how long it takes to actually just keep writing that base down there, okay? So as a general rule of thumb, you should always put the base in, except in a few different situations. So one situation is here. If I write log of x, it means that I understand that there is a base automatically implied. Now, annoyingly, that base can actually be two different things depending on who you ask, okay? So one thing it could mean is log to the base e of x, okay? So in other words, the base in this case is e. Now, it would be e if you ask a mathematician, okay? So in maths, it would be e, okay? And we've just talked about e very briefly, and I've kind of linked the video in the description talking about e in even more detail, okay? But it can also mean something else. It can also mean log to the base 10 of x. And that's if you ask a scientist. So by a scientist, I mean like a physicist, okay? So if you write log of x to a mathematician, that means log to the base e of x. To a scientist, that means log to the base 10 of x. So the question is, well, what should you use? Well, first of all, you need to be aware that on your calculator, so if I just bring my calculator up, there is a logarithm button. And can you see that that logarithm button is effectively here, okay? So that logarithm button's there. And if I just try write log, it's going to be log, it's going to ask for an input, so let's say 5, and it gives me an answer, okay? Well, what's the base in that case? Well, in that case, the base is 10. The reason being is because your calculator is a scientific calculator. In other words, it's looking at it from the perspective of a scientist. You know, the idea is scientists typically deal with massive numbers that are like order of magnitude of 10, like 10 to the power of something, if you ever looked at standard form, okay? Particularly when you're looking at like the size of the Earth, like the radius of the Earth is 10 to the 6 meters, I think, off the top of my head, okay? So it's always looking at a base of 10, right? So scientists tend to look at base of 10, whereas mathematicians, in this kind of context, tend to look in the base of e. So because your calculator is a scientific calculator, it's used for scientists. If you write log of 5, it's using the base as 10, okay? Now, just to make it a little bit clearer then, if I'm going to write log of x, so if I ever write down log of x on my page, don't worry about what the base is. Usually, I will always define what the base is, okay? So I would never usually write log of x unless I'm not interested in what the base is. So we're just about to look at laws of logarithms together. Now, in that case, I'm basically saying that as long as the base is consistent, as long as that growth factor is consistent, it doesn't matter what it is. So if I ever write down log of x, all I want you to think is, well, he's only writing that because it doesn't matter what that base is, okay? So just assume that because I don't care about what that base is, then I'm just going to write log of x, okay? Because it would work with any base, right? Now, if I do want to write down log to the base 10 of x, then I will write that. I could also write down log to the base e of x. So if I actually want that base to be e, I could write down log to the base e of x, okay? But in actual fact, I tend not to write that. Now, we've just seen that e is kind of the natural exponential number. It's the situation that describes natural growth. It's growth that is happening continuously, which is natural growth, right? So because it's growth that happens naturally, we call this the natural exponent, okay? This is the natural exponential number, right? So in a similar kind of way, because it's got e built into a logarithm, it's a logarithm that's talking about the natural type of growth or the natural type of decay. So in that case, we call this the natural logarithm. So we call it the natural logarithm. If it's got e as the base, we call it the natural logarithm. Now, because the guy that was looking about this, I think off the top of my head it was John Napier, but I would have to go away and double check this. He was French, okay? And the idea is that he took the n from natural and L for logarithm. Instead of calling it NL, okay, he calls it LN, okay? So if I ever write down LN, what I literally mean there is the natural logarithm. In other words, logarithm where the base is e. So I'd write down log to the base e of x, or the natural log of x, like that. Okay, so just be aware of that. It's just a little bit of notation, but it's really, really important. So let's have a quick look at laws of logarithms. Now, because I've basically said that there's exponentials and then there's logarithms, they're basically just the same thing, but looked at from two completely different perspectives. You remember that when we were dealing with exponentials, so in other words, things with powers in, okay, we had these things called laws of indices, which are basically like power laws, okay? And we looked at like laws of indices, things like, you know, if I have 2 to the power of x and I want to times it by 2 to the power of y, that's the same as 2 to the power of x plus y. Or if I had something like 2 to the power of x divided by 2 to the power of y, that would be something like 2 to the power of x minus y, etc., etc., etc. And you might have something like 2 to the power of x, all raised to the power of y, that should be equal to 2xy, okay? So these are all the laws of indices. And if I remember, I think there's about 7 of them, right? Which we went through together, okay? Now, just like we had, so these are all dealing with exponentials, right? So where the thing which is changing is in the power. Just like we've got laws of indices, laws of exponents, we've also got laws of logarithms, okay? So that's what we're going to look at right now. Now, I'm going to start you off with a couple of free ones, which don't really take much work, so logarithms. Don't really take much work to derive, okay? So if I write something like this down, so I'm going to actually write down log of 1, okay? So in this case, I'm just writing log with no base. That's just because I don't care what the base is. It can be any base you like, okay? Well, in that case, I'm basically saying something, so some base, let's say 3, to the power of what gives me 1. That's what I want you to think when I write that down. So whatever the base is down here, it could be 3 or 5 or 7, okay? Whatever that base is, if I raise it to the power of what, that should give me 1. Well, it should always be the case that anything to the power of 0 should be 1. So therefore, log of 1 should always be 0. Now, I'll give you another one as well. If I have some base down here, and if I have some size in here, okay, then basically saying a to the power of what gives me a? Well, laws of logarithms, laws of indices rather, you know that should just be 1. So a to the power of 1 should be a. So in other words, you're just simply asking the question, a to the power of what gives you a? The answer is 1. So these are kind of a couple of free ones, okay, which I always kind of start off with to kind of ease you in. But let's actually break this down. So let's actually have a look. Let's suppose, okay, I want to consider something like this. So I'm going to go log to the base 2 of a. So I'm going to write a base of 2 in. Okay, it doesn't actually matter what the base is. So I could actually generalize this to log of a if I wanted to. But just for the sake of proof, I'm going to keep the base as 2. And I'm going to add on log to the base 2 of b. So still the same base, still the same growth factor, but this time the sizes are different. So the a and b is different, and I'm adding the two logarithms together. All right, so what I'm going to actually start off by doing is I'm going to look at these two logarithms and I'm going to give them a special name. Okay, so I'm going to look at log to the base 2 of a, and I'm going to look to log to the base 2 of b, and I'm going to give each of these a special name. Okay, so I'm going to say, for example, this one is x and this one is y. Okay, so I'm just going to give them a name just to allow me to work with them. And what I'm going to try and do is relate it to things we've already looked at, i.e. laws of indices. Okay, so let's have a look. Okay, so if I wanted to convert these two things, would you be happy that if I looked at x equals log to the base 2 of a, if I converted that back into an exponent form, well, in that case, the a, or the 2 is the base, so I'm going to write that as 2 is my base, the power is x, and the size is a. Okay, so the base, the growth factor is 2, the power, because remember logarithms are all about looking at the power, that's to the power of x, and then a, that's my size. Okay, good. If I do the same thing for the y logarithm then I'm going to have 2 to the power of y is equal to b. All right, good. So I'm going to use that. Okay. So let's have a look at this then. Let's have a look at this. So just consider this then. So because I've let log to the base 2 of a just be x, I've let that equal x up there. So I'm going to write this as x down here. Okay. And likewise, because I've let log to the base 2 of b be y, then I'm just going to write this as y down here. So in other words, I just have x plus y. Okay. Now what that means, I'm able to then work with it quite nicely. Because I know an indice law where I'd have to add the powers. Notice on this right hand side, the x and the y are really powers, okay? So I know an indice law where I'm going to have to add those powers together. Namely, if I have 2 to the power of x times by 2 to the power of y, well, that should give me 2 to the power of x plus y, okay? So that's basically an indice law which I've noticed where I'm going to end up adding x and y together. So let's break this down, okay? So I know that 2 to the power of x, well, that's just going to be a, okay? So 2 to the power of x is a. I'm going to times that by 2 to the power of y, well, that's going to be b, okay? So I'm going to times that by b, and that should be 2 to the power of x plus y. So now if I work with this thing in red over here on the right-hand side, okay, and if I put this back into logarithm format, okay? So on the left-hand side, I've got ab. On the right hand side, I've got 2 to the power of x plus y. If I put this back into logarithm format, I'm basically saying my power, i.e. x plus y, should be log, well, my base is 2, of my size, which in this case is ab. So just simply by looking at that thing on the right hand side, I've got x plus y is log to the base 2 of ab. Okay, now have a look at this. I've basically said that this thing here, my log to the base 2 of a plus log to the base 2 of b, that is just simply x plus y. And I've just proved down here that x plus y is just log to the base 2 of ab. So in other words, this thing here is just going to be log to the base 2 of a times b. Okay, so that there is your first law of logs. Okay, in fact, I'm just going to get rid of all of this so it doesn't then distract from what we're doing here. So have a look. I've basically said that if you end up adding two logarithms with the same base together, so log to the base 2 of a plus log to the base 2 of b, that should be the same as taking that same logarithm with the same base, so log to the base 2, but this time I times those two a and b together, okay? Now if you think about it, this is a nice analogy, okay, this is a nice analogy to if I take some base, let's call it b, to the power of x, times by the same base to another power, that should be equal to the same base to the powers being added together, okay? So just remember that exponentials are all about the powers, logarithms are all about writing things so that the power is the subject. So that thing there is really talking about a power, okay? So log to the base 2 of a is basically saying, what is the power when I have a base of 2 and the size is a, okay? And likewise this thing here, it's talking about the power. So because I'm literally on the left-hand side just adding two powers together, a logarithm is just like a power, okay? I'm adding two powers together, that's equivalent to timesing in the bases, okay? And you can see that multiplication happening over there. So times, add, you can see the same thing happening here, add, times, okay? Now I can do the next one really straightforward and easily as well. By the way, I'm just going to get rid of that 2. Just because it doesn't actually matter what the base is, like I say. So log of a plus log of b equals log of a times b as long as the base is the same. Let's look at the next one then. So if you remember, there's another analogous sort of law of indices here, which is where you divide, okay? So I'm going to say, well, okay, if I have log of a, take away log of b. In other words, I'm subtracting in the powers. So again, because I've said log, well, let's say log to the base 2 just for the sake of argument for the time being. So I've got log to the base 2 of a minus log to the base 2 of b. Well, I've said log to the base 2 of a is x, okay, so I'm going to call that x. And I'm subtracting, well, log to the base 2 of b, that's going to be y, okay, so I'm subtracting y there. So let's just think, okay, if I look at two things which I know are subtracted, look at using the laws of indices, I'm basically saying, well, okay, if I have 2 to the power of x divided by 2 to the power of y, that should be equal to 2 to the power of x minus y. Well, are you happy that 2 to the power of x is just a and 2 to the power of y is just b? I'll let that equal that up there, okay? So therefore, I get a divided by b, okay, equals 2 to the power of x minus y. Instead of writing a divided by b, I'm actually just going to write that as a over b, right, as a fraction instead. And that's got to be equal to 2 to the power of x minus y. So now if I put this back into logarithm form, my exponent, my power if you like, is x minus y. And I say my logarithm with my base of 2 should be the same as a over b. So I'm literally just taking this thing and converting it back into logarithm format, okay? We'll have a look. This thing here is literally just x minus y. I've said that. So in other words, this thing should just be equal to, well, log to the base 2 of a over b. Right? So again, this thing here is analogous. So I'll get rid of all of this kind of proof, or my argument down here, which I've used. I'll get rid of this as well. This is kind of analogous to saying, well, if I have some base and I raise it to some power, and if I divide it by the same base to a different power, that should effectively be equal to the same base with the powers subtracted. So have a look. I'm subtracting in the powers. Remember, logarithms are looking at it from the perspective of power. Subtracting in the powers, I'm dividing in the bases. Okay, so similar kind of thing to that going on. Now there is one other final little law which I want to look at, which is this one. If I have some constant, let's say a, and I times it by log of b. Okay, so again, actually I'm just going to get rid of the base 2's of all of these because it doesn't actually matter what the base is. So in general, log of a minus log of b equals log of a divided by b. Let's look at number 3 then. So if I have some constant a and I times it by log of b, so I don't care about what that base is. Okay, let's see what this is equal to. I'm going to do it with an example. Okay, so let's suppose we have 3 times log of 2. Okay, so just think, what does 3 times something mean? Well, 3 of something just means 3 times the thing, means add itself 3 times. So this just means log of 2 plus log of 2 plus log of 2. Okay, that's literally what 3 of something means. It just means add the thing to itself 3 times. Well, I've just seen a law of logarithms. Look at my first law of logarithms. Basically, if I add together logarithms with the same base, I should just times the things inside the brackets, okay? So I should times these things down here. So this thing here should be log of 2 times 2 times 2, okay? Well, what is 2 times 2 times 2? I could write that as 2 cubed. So let's see where we started, okay? In this case, we started with 3 times by log of 2, so exactly the same kind of setup as I was looking at in my general case, so some constant times by log of some number, and I ended up at log of 2 cubed, okay, so log of 2 cubed, okay, so look what's happened here, okay, the log and the 2 have kind of stayed the same, but the 3, which was originally out the front, has now climbed up to become the power of the thing which I'm taking the logarithm of. So in general then, what I can say is that a log of b should just be equal to log of b cubed. In this case, sorry, log of b to the power of a, because in this case, my a is here and my power is going to be up there, okay? So in other words, the power just climbs up. Now, an analogy to this would basically be saying if you have b to the power of x and you raise the entire thing to the power of y, then I just simply need to multiply those powers together. So have a think about why that's analogous. Look, I've got b to the power of something. That's a bit like saying b to the power of something on that side, okay? And then effectively, I end up multiplying those powers together. There's a multiplication of those powers together. So it's a bit analogous to that. You've got to kind of look at it loosely, but literally that's how it works, okay? So there we go then. Those are the 3 main laws of logarithms that we need to have a look at. We need to have up our sleeve. So log of a plus log of b is equal to log of a times b. Log of a minus log of b is equal to log of a divided by b. So are you happy that the first 2 laws of logarithms are quite easy to remember, because it means, okay, if I'm adding logarithms together, it means I can times, okay? And there's an analogy there with laws of indices. Same thing, laws of logarithms 2, that's basically saying if I subtract those 2 logarithms together, there's an analogy with divide as well. So add, times, subtract, divide. And then this one, I tend to find is quite easy to remember, because if you can basically take a constant out the front and stick it up as the power inside the logarithm. Now just be aware here, because this is really kind of quite crucial, if I have like a log of b, that is not equal to log of b all cubed, all to raise to the power of a, okay? So in other words, it's not basically saying that the a is climbing up to be the power of the entire logarithm, it's just basically the power of the thing that I'm taking the logarithm of, so in this case the b, okay? So just be aware of that. It's an easy trap to fall into, but just be aware that that is not the same, okay? Now let's look at a very, very quick question then. All right, so let's have a look at this question here then. So 2 log of x plus log of 2 equals log of x plus log of 3. So first things first, I'm just going to go through and I'm going to try and find out any laws of logarithms that I can do to simplify this, make it easier to deal with. Well, straight away, look, 2 log of x. Now, notice I'm using log of something. That log of something just means that I just assume that the base is the same. So don't worry whether it's base 10 or base e, don't get confused in that sense. Just say, okay, log of something, I just basically mean the base is the same. Okay, so in this case, 2 log of x. Well, do I know a logarithm that I can use to simplify? Yes, I do. Okay, in this case, law of logarithm 3, look, a log of b should be equal to log of b to the power of a. Well, I can use exactly the same law there. So I can basically say this thing is just log of x squared. In other words, the 2 climbs up to become the power, okay, and everything else is still the same. So plus log of 2 equals log of x plus log of 3. All right, good, that's good. So now let's have a look at this. So let's have a look at the left-hand side, okay? So I have 2 logarithms with the same base that I'm adding together. I think law of logarithm 1 would work there, okay? So 2 things with the same base added together just means I can basically multiply inside there, so condense it down to a single logarithm. So this thing here is going to be log of, well, x squared times 2, which I can write as 2x squared, okay? And similarly, on the right-hand side, I have log of x plus log of 3. Again, I'm going to times those 2 things together. So I'll end up with log of 3x. Okay, so condensing it down to a single logarithm. Now, if you're looking at this and going, well, where do I go now? Like I've got log of 2x squared equals log of 3x. What do I do next? Okay, well, that's fine. It's actually, you've done all the hard work already. You've used all your law of logarithms. You've got it simplified to this point. And in general, when you're solving laws of logarithms, you really want to get to this point. This is kind of a really good thing because it basically is saying, look, I've got a single logarithm on the left-hand side, single logarithm on the right-hand side. So log of something has to be equal to log of something. Well, the only way those two things can be equal is if those two somethings, the two things that I'm taking the logarithm of, have to be identical. In other words, that thing has got to be the same as that thing on the right-hand side. So 2x squared has got to be the same as 3x, otherwise they're not going to be identical to each other. Now, this is effectively the equation which I'm solving, and we've solved equations like this hundreds of times. Now, just be careful here, because the temptation would be to just divide both sides by x. In other words, you just get 2x equals 3 and you solve that to find x equals 3 over 2. However, look at this equation, okay? This equation is an order of 2. Look, there's an x squared there, which means that I'm expecting two solutions here, if possible, okay? So I'm expecting two solutions. So don't just divide both sides by x. That's a really bad move. In order to capture both of the situations, I can see it's a quadratic. What do we always do to solve quadratic equations? Well, we make them equal to 0. So I'm going to stick the 3x on the left-hand side, okay? So I'm going to end up with 2x squared minus 3x equals 0. Okay, so 2x squared minus 3x equals 0. Now I'm going to factorize, okay, so I'm going to factor out an x, and inside I end up with 2x minus 3 equals 0. Well, okay, I've got two things being multiplied together. They equal 0. That means that either x equals 0 or 2x minus 3 equals 0. And there we go. So that's my x equals 3 over 2 on the right-hand side. So basically, my two solutions are x equals 0 or x equals 3 over 2. Except they're not. And here's why, okay? If you come right the way back up here, and we did it a little while ago, so let's just refresh our memories. When we looked at the logarithm graph, look at the domain and the range. We literally said that domain has to be a value which is strictly positive. We looked at the value has to be strictly positive. The output we didn't really care about, it could be anything you like, but the input has to be strictly positive. In other words, we're not allowed 0 or negative. So if we actually have a look at the logarithms in our questions, which is here, okay, so this was the original question that we were looking at. So if you look at the logarithms on our original question, we had log of x and we had log of x, okay? So these are the two logarithms we had in our question. So in other words, in that case, I'm saying that in order for this to work, and I'm going to draw this out as a little table, the logarithm that we were dealing with was log of x, which basically means that the input, the thing we're putting into that logarithm, in this case the x, has to be positive. It cannot be negative and it cannot be 0. Okay, so let's just check our two values of x. So our two values of x, remember, were x equals 0 and x equals 3 over 2. Okay, so when we stick that into our logarithm, let's check. Well, when we stick x equals 0 into our logarithm, are you happy that x is not positive? X is not greater than 0. So therefore, that value there will strictly not work. So if we stick x equals 0 as our solution into our logarithm, it won't work. It has to be positive. Now, if we stick x equals 3 over 2, well, that's 1.5-ish, okay? If we stick, well, it is equal to 1.5, sorry. If we stick that into our logarithm, is 1.5 positive? Yes, it is. So therefore, the only solution which you are going to get is x equals 3 over 2 only. Okay, if you put down x equals 0 or x equals 3 over 2, you will not get full marks. You have to deduce that actually you can only put positive values into this logarithm. The thing you're taking the logarithm of has to be positive, okay? So always check your solutions to make sure the input is positive. If it is, then keep that solution. If it's not, you have to get rid of it, okay? So hopefully that makes sense.